Alright, in this section we're going to talk about section 2.1, using fundamental identities. What an identity is a statement that's true no matter what you plug in for the variable. So looking at this first part of the table of identities that's on your paper, just looking at sine of u. Sine of u is going to be equal to 1 over cosecant of u no matter what. So you could put 0, pi over 2. It doesn't matter what you put in for u, that statement's always going to be true. So that big long list, all of those things are true, and since they're always going to be true, we're going to be able to substitute them in and out depending on how we see fit. So sometimes we might want to look at secant just as secant of u. Other times it might be useful to look at secant of u as 1 over cosine of u and get some things to cancel out. So we're going to be able to interchange these things any way we want, any time we want, because they're going to be equal no matter what that value of u is. So everything you see on the screen right now, so the top half of that table, you need to have memorized. The bottom half and anything else we get moving this point forward, I will give you on any test or quiz a sheet with those identities, but the ones that you see in front of you right now, you have to put to memory. Now, another thing that we want to say, or I want to say about this is, if we look at the Pythagorean identities, we're allowed to add and subtract. So if we want to subtract a cosine to the other side, we're allowed to say sine squared of u is equal to 1 minus cosine squared of u. So we can manipulate these in any way we want. The 1 plus tangent squared u equals secant squared u, and the 1 plus cotangent squared u equals cosecant squared u actually come from taking our original Pythagorean identity and dividing everything by either sine squared or cosine squared to get one of these two things. So we're allowed to manipulate these any way we want and still make that substitution. So all of these ones here you have to have memorized. The rest of that table, these ones here, I'll give you on any assessment that we're going to be doing. So how we're going to end up using these things is a little bit different. There's not a set way that we're going to use these every single time. It's going to depend on the question. It depends on what we're going to be looking at. So if we see this first example, simplify sine x times cosine squared x minus sine x, we want to simplify. So the first thing that we're going to want to think about is, can I factor anything out? So I have a sine and x in the first one, I have a sine x in the second one, so we can factor out a sine of x. So that's going to leave us with cosine squared x minus 1. Now, a general rule of thumb, whenever you're dealing with trigonometric identities, trigonometric expressions, equations, if there's a square, Pythagoras might be right around the corner. So if we think about our Pythagorean identity, sine squared plus cosine squared equals 1, if we mess around with this one, if we say subtract 1 from each side and subtract sine squared from each side, we know that cosine squared x minus 1 is the same thing as negative sine squared x. So we're going to make that substitution in here. So we're going to say sine of x times negative sine squared of x, and this is going to simplify into negative sine cubed x. Now the only reason we wanted to make that substitution is because we had a sine already, and sine times sine is just going to make this a little bit easier. If this turned into something like tangent, that's not going to help us with sine at all, so we're just going to leave it. We would leave it there if it was something like tangent or whatever. But since it gave us a sine, we're going to go ahead and simplify that. So that's one way we can mess around with these things. If we look at this one, this is just going to be factoring just plain and simple. So this one really isn't using identities at all. It's really just thinking about this as something like this, 4x squared plus x minus 3, except instead of x we have tangent. But we're going to treat it the same way. So if we were going to factor this out, we would end up getting 4x minus 3 and x plus 1. Well, that's not x's, those aren't x's, those were tangents, so we're really looking at 4 tangent of theta minus 3 and tangent of theta plus 1. And the reason we would want to do something like this is eventually we're going to solve equations. So if this were set equal to 0, we'd want to factor it so we can set each of these pieces equal to 0. And that's mainly what we're doing here. We're just trying to simplify these things so we can solve. That's the big goal in this unit, is try to write these things in such a way that we would be able to solve an equation if we had to. So a couple more examples, and then we'll call it quits on the video. So example 3, simplify cosecant squared minus cotangent minus 3. Now this one's not quite as easy because we can't just treat it like this. That's not going to work because cosecant and cotangent aren't the same thing. This would be more equivalent to something like this. X squared minus y minus 3. Because our variables would be different, our cosecant's not the same thing as cotangent. But if you remember what I mentioned earlier, anytime there's a square, Pythagoras might be right around the corner. On that last problem we did, we didn't have to worry about the square because our tangents were already in agreement. So Pythagoras might have popped in, but since our tangents were already in agreement, it didn't matter. Now what we're looking at, the cosecant and the cotangent aren't related. So if we look at the Pythagorean identities that we had before, we can manipulate, or I guess we don't need to manipulate because it's already been done for us. We can look and see that cosecant squared of x is going to be equal to 1 plus cotangent squared of x. So we can make that substitution in here for cosecant of x. We're going to get 1 plus cotangent squared of x minus cotangent of x minus 3. Combine our like terms. So we're going to be looking at cotangent squared of x minus cotangent of x minus 2. Now since our cotangents agree with each other, we can think about this just as x squared minus x minus 2, because we have the agreement now. And if we were going to factor that, we would get x minus 2, x plus 1, but we don't have x's, we have cotangents. So really our answer is going to be cotangent of x minus 2 times cotangent of x plus 1. So again, we want to get these things in agreement with each other. We want to have either all cotangents, all cosecants. That way, if we had to solve, if this thing were set equal to 0, we can set each piece equal to 0 and solve. So next thing we might want to look at is something like this. Simplify sine of t plus cotangent t cosine of t. So there's a lot of stuff going on. We have a sine, we have a cotangent, we have a cosine. 3 terms, or 3 types of terms. That's way too many. So another rule of thumb is, first one being if we have squares, Pythagoras might be showing up. The second one is cotangents and tangents, if they're in the same problem with sines and cosines, let's rewrite them in terms of sine and cosine. So we can write that as sine of t plus cosine of t over sine of t times cosine of t. So cotangent equals cosine over sine. That's one of the things we have to have memorized. Now we can kind of combine these things here. So we're going to be looking at sine of t plus cosine squared of t over sine of t. And that looks a little bit better. It might not because we have like a fraction here, but to me it looks better because we went from sine, cotangent, cosine to just sine and cosine. But we can go a little bit further, right? This is going to be sine over 1, so we can get a common denominator of sine. So this is going to be the same thing as sine squared of t plus cosine squared of t over sine of t. So now we have a couple of squares in our numerator, and if we go back to our Pythagorean identity, because we have squares, sine squared of t plus cosine squared of t equals 1, so we can make that substitution, make this 1 over sine of t, and 1 over sine of t is cosecant of t. Alright, our next example is going to be something similar to what we just did. We have 2 fractions that we're trying to add together. So we need to get a common denominator. So our common denominator is going to be 1 plus cosine of theta times sine of theta. So in order to get that common denominator, we need to multiply this first one by sine over sine, so we're going to end up with sine squared of theta. We're going to need to multiply this one here by 1 plus cosine of theta, so plus 1 plus cosine of theta times cosine of theta. And that's going to be over our common denominator, 1 plus cosine theta sine theta. Now, we can play around with this a little bit. We can distribute our cosine through, so we're going to get sine squared theta plus cosine squared theta plus cosine to the third theta. Oops, I made a mistake, sorry. This is not a square, right? It's just a plain old cosine. So this is just a plain old cosine. And that would still be cosine squared. So distributing the cosine through, we get cosine times 1 would give us this cosine here. Cosine times cosine will give us cosine squared. So we're going to end up here. I made a mistake up here. And that's still going to be over 1 plus cosine of theta over times sine of theta. Well, we have squares, so we got to be thinking about Pythagoras. We know sine squared plus cosine squared is equal to 1. So that turns into 1 plus cosine of theta over 1 plus cosine of theta sine of theta. We can cancel out our 1 plus cosines of theta, make this 1 over sine of theta, which is cosecant of theta. So once again, that last problem was cosecant of theta. It looked really weird at the beginning, and now we have another one that's going to end up at cosecant of theta. So the whole thing here is, again, we just kind of want to play around with these things, see how simple we can make them look. Now, the last one, not quite sure why we would want to do this, other than the fact that it's a fun little exercise. But rewrite 1 over 1 plus sine of x so that it isn't a fraction. So 1 plus sine of x, not a fraction. So we know that a way that we can get rid of a sign, turn a sign into something else, is if it were a squared. So a trick that we've had in the past to try to get something out of a denominator, it usually turns something into squared, is to multiply by its conjugate. So if we multiply by the conjugate here, we're going to end up with 1 over sine of x over, so 1 times 1 is 1, negative sine of x, positive sine of x cancel out, minus sine squared of x. I see a square, so that means Pythagoras is probably around here, so we start out with sine squared of x plus cosine squared of x equals 1. I have a 1 minus sine squared of x, so I know that cosine squared of x is equal to 1 minus sine squared of x. So I can rewrite this as 1 minus sine of x over cosine squared of x. You're probably asking yourself, what was the point of that? This is no more simple, it's still a fraction, but what we can do now that we couldn't do before is split this into 2 separate fractions. Before we had 2 terms in our denominator, we couldn't do anything about it. Now we have 1 term, so we can write this as 1 over cosine squared of x minus sine over cosine squared of x. 1 over cosine squared of x is just secant squared of x. We can think about sine over cosine squared as minus sine over cosine times 1 over cosine. So we're looking at secant squared x. Sine over cosine is tangent of x. 1 over cosine is secant of x. So now it's no longer a fraction. And that's what the question was asking us to do. So there's a bunch of different things that we talked about here, a bunch of different ways we can use our identities, certain things that we want to look out for, like squares. We're going to be using these quite a bit, so we'll see you in the next one. That'll do it for this video.